Hey guys, how you doing? So welcome to the second video for chapter 6. In this video we're going to take a look at homeostasis. We're going to look at a few different areas, particularly around body temperature, metabolic rate, and then also we're going to look at blood glucose level as well as a few key examples of homeostasis. So let's jump into it. Okay, body temperature. Now organisms are categorized according to how they get their body heat. Okay, we have two different categories. We call them endotherms. Endotherms, endo meaning inside, thermic or thermos meaning heat, get their heat from their own metabolism, and these are your warm-blooded animals that you and I assume, although warm-blooded is technically not the correct term because what we mean by warm-blooded is that animals that are able to regulate their own body heat. Okay, so mammals are a really good example. And then you've got your ectotherms, ectotherm meaning outside, thermos meaning heat. They get their heat from the outside or their surrounding environment, and they are what we think of typically as your ectothermic, cold-blooded animals, your reptiles and your insects and things like that. Okay, here's a heat signature between the rat and the cobra. Right, you can see there, the brighter the color, the more the more heat the organism or whatever it is has, and you can sort of see there the external environment sits at this kind of a violet or purple kind of color. You can see the rat is very bright orange, showing that it's got its own body heat, and then the cobra being very similar to the external environment, just perhaps a little bit above the external environment heat, right? So endothermic organisms that get the heat from their own metabolic process are coined warm-blooded, even though it's not technically correct. Endotherms use a proportion of the energy from their food and turns it into heat, which then warms up the organism. Now, for most endotherms, that sits at about 50 or 60% of the metabolic energy that they get from their food. It's a very inefficient process, but it keeps them warm and helps us survive. It also means that for an endothermic organism, the energy demands is much higher to remain active all the time, because your body and my body needs to sit at 36.7 degrees. It also means that our body continually loses energy in the form of heat to keep it at that stable range, which means you and I eat more frequently. All mammals and birds are often endothermic, and what we can also do is we maintain that temperature at a constant rate. Now there's a different term for that, even though they're very closely related, and that term is called homeothermic. Homeo meaning same, thermic meaning heat, and so they have the same or a constant core body temperature. These terms are different, but most organisms that are endothermic are often also homeothermic. So we are both endothermic and homeothermic because we get our energy from our metabolic processes, and also we keep our core body temperature at a stable 36.7 degrees. Okay, this also means that we eat fairly frequently. We eat about 3 times a day, and most animals and birds need to eat very often in order to maintain their own body temperature at that rate. It also means we can be active at all times of the day, whether it's during the morning or at night, even though for some students that's not true. Okay, your ectotherms, ecto meaning outside. So ectotherms get their heat from the surrounding environment, which also means other sources such as the sun, a really nice warm rock early in the morning, a warmer area or warmer body of water are often ideal places for ectotherms to settle or to gain their energy, because they then are able to warm up and then perform the activities that they normally do during the day. There's a trade-off here. It means they eat less than endotherms in order to survive. You know, one meal for us might last a couple of hours, and then we have to eat kind of 3 times a day. One meal for an equivalent animal of our size, for example, you know, a fairly small crocodile, for example, might last them about, you know, a week or so without having to eat again. And so all reptiles, amphibians, fish, and invertebrates are ectotherms. Okay, there's a second term once again, which is called poikilothermic. Poikilothermic organisms have a variable core body temperature, which means their core temperature fluctuate fairly frequently. And so once again, the terms are different, but most organisms that are ectothermic are also poikilothermic. Okay, there's a few examples of organisms that are ectotherms, but are not necessarily poikilothermic, but are rather homeothermic. One good example are actually dinosaurs. So dinosaurs are ectotherms. In other words, they get their heat from the surrounding environment. But because dinosaurs were so large, they had a very low surface area to volume ratio. And also on top of that, they've got more hemoglobin and red blood cells and things like that than your regular reptiles. And as a result of that, dinosaurs, particularly the really large ones, were often ectotherms, but they were homeothermic because the large size retains heat at a constant temperature despite fluctuations throughout the day. And so the larger the animal, the more ideal it is that it can maintain a core or a stable body temperature. Crocodiles are also a really good example of that. Crocodiles are ectotherms, but they, to an extent, have a homeothermic kind of body temperature as well. Now, activity, take a look at this graph here of the red-bellied black snake. You can see the red-bellied black snake is an ectotherm, and this is the pattern of its energy levels throughout the day and throughout the night. You can see there at the start of the day, it will retreat, and then in the morning it will go to a location where it can bask in the sunlight, allowing its body temperature to increase. And what the snake will do is that initial heat energy will then allow it to kind of do whatever it wants throughout the day. It will slowly lose energy, and then it will move back into the sun, gain energy, and it will periodically do that throughout the day in order to maintain its temperature within that range of roughly about 25 to 35 degrees Celsius. And then what happens is at dusk it will crawl into a log or some sort of shelter, and then the body temperature then starts to drop again throughout the night, and then resuming back again the next day, it will go back into the sun again. So you can see there, that's the ectothermic nature and the poikilothermic nature of that fluctuation throughout the day, and then fluctulation bigger or a larger fluctuation throughout the night. Okay, and so in terms of energy expenditure, you can expect that the ectotherm will spend less energy overall, joules representing the unit for energy. And then you can see there the range of body temperature that the organism can tolerate is a lot wider, yeah? Meaning it uses less energy overall, but the body temperature fluctuates at a higher rate. You can sit anywhere between 5 degrees all the way up to 35, 36 degrees Celsius. And so they are able to tolerate a wider temperature range. However, they don't or can't expend as much energy as an endothermic organism can. So a reptile like a lizard will never be able to burn as much energy as a mammal can. However, they can tolerate a wider range of environments, whereas your mammals often can't do that, right? And so your mammal or your endotherm will only really be able to tolerate down to about 30 degrees before it starts to really undergo physiological stress, and then it will peak at about 40 or so something degrees. But within that narrow range, it can be pretty active the whole time because it's very good at maintaining the amount of energy that it burns in that particular time frame. Okay, so in terms of your endotherm and your ectotherms, you can see their energy consumption coefficient. Your fish are pretty terrible. In other words, they use the least amount of energy for their mass, and then as you sort of move your way through, you get to your more warm-blooded organisms and also your larger organisms because they're both larger and they begin to consume more energy as a result. Okay. Oops. Sorry, guys. For the same size, however, you would expect that warm-blooded animals such as birds and things like that will often use more energy in terms of the coefficient at the same size. So a rat compared to perhaps maybe a lizard of the same size, the rat will expend so much more energy than the lizard, even though they're about the same size in terms of their mass, right? And you can see the bit of the anomaly there is the bumblebee. The bumblebee, even though the bumblebee is an insect and is technically an ectotherm, it has a really good method of warming up its body. And what it does is it actually vibrates quite rapidly. And that vibration of the wings allow it to burn a lot of energy as a result and then warm its body up. And so bumblebees actually can maintain a fairly stable body temperature, even though they're so small and even though they're ectotherms and they can't really do what mammals do in terms of metabolic heat. Okay. In humans, core body temperature must stay at about 36.7, and the hypothalamus is the body's thermostat. Yeah, your hypothalamus, which sits at the back of your brain and regulates that, is what allows your body to identify that, yep, your body temperature is sitting at a stable rate, or oh no, it's falling outside of the body temperature rate. And so it controls all of the different parts of the body that allows it to regulate that body temperature. So here's a diagram with an example of that. Yeah. So a cold environment causes heat loss, and then the body temperature, or the core body temperature, falls. The hypothalamus will receive that information about the temperature fall, and a few different things can happen. Yeah. It can activate warming up mechanisms, and there's a few. First of all is behavioral changes, for example, putting on more clothes or jumping up and down, which then reduce your heat loss, your body temperature rises, and that's the kind of the ideal outcome. A physiological change could be your motor neurons relay messages to your skeletal muscles, and then the muscles will then contract and release, causing you to shiver. That shivering generates heat, increases your heat production, and then your body temperature rises. Your skin arterioles will constrict, causing a vasoconstriction of the blood vessels, reducing the amount of heat being lost from your skin surface, and therefore your body temperature rises. A hormonal change, which is also another physiological change, could be the cells in your hypothalamus produces TRH, right? And so the TRH is a thyroxine hormone. Thyroxine hormone then increases your metabolic rate, and then then causes your body temperature to increase again. Okay. So that's some of the methods. Now, what happens if your body temperature falls outside of that range for a long period of time? The mechanism can't be maintained, and basically your homeostasis fails. Yeah, and so you kind of got two terms for that. You got hypothermia and hyperthermia. Hypothermia is when your body temperature falls below the tolerance limit, and hyperthermia is when it rises above. Hypo meaning low, hyper meaning high, right? And so when you go through hypothermia, your body's being cold for too long, and then it starts to shut down. Hyperthermia means it rises too much, and then it goes through physiological stress, right? In cold environments, hypothermia is what kills you the most. Yeah. For example, in the movie The Titanic, which is a bit of an exaggerated representation anyway. However, yeah, the ever popular scene of when Jack and Rose are sort of both in the water, and then everyone is kind of floating in the Atlantic Ocean. And in real life, actually, during the sinking of the Titanic, it wasn't the drowning that killed most of the people. It was the hypothermia within the Atlantic Ocean. And so the reason why Jack dies, theoretically, is because he dies of hypothermia, being in the water for a prolonged period of time. Homeostasis fails, and he dies. Rose, on the other hand, gets put on the extremely large kind of floating raft that can fit two people, but she survives because her body temperature stays at above the limit. Another good example, hypothermia is a really big killer of a lot of snow expedition, ice expeditions as well, because the snow or the ice is over a long period of time, homeostasis fails, the body falls below the limit, and then the person or the organism or the dog dies as a result. Okay. Your thyroid. Now let me talk about your thyroid. What does your thyroid do? Your thyroid is particularly important because it is responsible for a particular hormone called thyroxine, which increases your metabolic rate. So your thyroid is a gland, or your pituitary gland releases a particular hormone called a thyroid stimulating hormone, or TSH. The TSH hormone causes your thyroid to release thyroxine. Thyroxine is a chemical, right? And thyroxine is the chemical that increases your cell's metabolic rate. And so what happens is when you release thyroxine, your metabolic rate increases, right? And so it counters that change. So by releasing your thyroxine, your body increases its metabolic rate. However, there are a few issues with that. If you have a condition called hyperthyroidism, it means that there is an increase above the recommended rate. So as a result, the person will have a faster heart rate, sweat more often, and feel cold. Will feel hot even though they are sitting in cold conditions. And so that's hyperthyroidism. Hypothyroidism is when you have the opposite, severe decreases in basal metabolic rate. And as a result, the person has a drop in heart rate and becomes sensitive to cold conditions. So often hypothyroidism will happen when people are deficient in iodine, which is the kind of stuff you get in fish, or perhaps maybe if you have a severe swelling of the thyroid gland, often called a goiter. And what that means is the person experiences hyperthyroidism or hypothyroidism because their thyroid gland isn't working properly or is working overtime as a result of that. Oops, sorry, went too far. So, a person with hyperthyroidism will often feel really hot, even though everyone around them feels cold. A person with hypothyroidism will feel cold, even though everyone around them is sweating, right? So if left unchecked, often it can create, issues around the body's metabolic rate, and also keeping warm or staying cool, okay? Homeostasis in terms of your body fluids. So there's a term for that called osmoregulation, similar to the word osmosis. Osmoregulation is the ability to regulate body fluids. Yeah, because all metabolic processes happen in water, your body needs to maintain your fluids at the right level. You can't have too much water and not enough ions. Can't have too little water and too much ions. Otherwise, it fails. And so the hypothalamus regulates that. The water reabsorption by a particular hormone called ADH. ADH stands for anti-diuretic hormone. So ADH travels through the bloodstream to the kidneys, and it makes the collecting ducts of the kidneys more permeable to water. What does that mean? If you did the excretory system in chapter 4, what that means is your body reabsorbs more water from the liquids that you drink and that you take in, your water intake. If you have more ADH, it means your body reabsorbs more water from the liquids. If you have less ADH, then less water is reabsorbed and it gets released, okay? So basically, if water levels in your blood, it drops too low, ADH is released, and then it releases a sensation of thirst is triggered. And so ADH is released, your kidneys start to reabsorb more water, and then also stimulates that feeling of thirst so that you drink more water as well as a result. If water levels are too high, ADH is inhibited. In other words, it's held back and not released. And it's that feeling of thirst is being suppressed, right? And so that is another method in which your body regulates that. And so a couple of drugs and things you take can actually interfere with that process. So, for example, caffeine inhibits ADH. And so what happens is when you drink a lot of coffee, you often find that you get dehydrated as a result because the coffee inhibits the release of ADH. And so what happens is your body doesn't realize that it's losing water, and so it doesn't reabsorb the water from your kidneys, and as a result you kind of pee out a lot of water and you start to pee heaps, and then you become really thirsty for all of a sudden because when the caffeine wears off, your body then starts to realize, oh no, you're extremely low in water in your blood as well. And so caffeine is actually is an anti-diuretic. It causes your body to retain a lot of its the ADH, and then it kind of screws you over a little bit there. Okay, so here is the negative feedback loop showing how this homeostatic mechanism works. So if you have a decrease in water level or an increase in solute concentration of body fluids, now what that means is either if you don't drink enough water or if you eat food that is really salty, your osmoreceptors in the hypothalamus will detect some sort of change. Basically, your brain starts to realize, oh no, water levels have decreased or salt levels have increased. Then that is a nerve response or a receptor response in the hypothalamus, sends it to your hypothalamus, and your hypothalamus then releases ADH, and it also signals the thirst center in your brain, which stimulates your body to become thirsty, right? And that is the effector. The effector is your kidneys, or your kidneys tubules more specifically, to become more permeable, reabsorbing more water. Your thirst center in your brain is stimulated, and therefore your mouth starts to feel really thirsty. And then the response is that increased water reabsorption in the kidneys, decreased urine volume, and also your increased water uptake by drinking. And then as a response, the fluid levels feeds back into your body, and therefore increases to counter that change. And that, once again, is a negative feedback loop, as indicated by that symbol there. Okay. If water levels are too high, you get the reverse effect. Everything kind of is the same, except your hypothalamus then inhibits ADH, and therefore your kidney tubules become less permeable to water. Basically, you churn more water out of your pee, increases water urine, the water in the urine, and expels more water as a result of that. Which is why when you eat too much salty foods, you will find your pee turns yellow. If you have a lot of water, you drink a lot of water, your pee turns clear because your body is actually increasing or decreasing the amount of water it's reabsorbing from the drinks that you drink or the food that you eat, right? And so that's why they say, if you got a bit of a yellow pee for a long period of time, you really should be drinking or increasing your water uptake. If it's clear, you're in the all clear, and your body's not stressed out too much as a result of that. Okay. Lastly, I want to talk about homeostasis in terms of blood glucose level. So glucose is really important for cellular respiration, and a healthy glucose level sits at around 3.9 to 5.5 millimoles per liter. In other words, 3.9 to 5.5 millimoles of liter of blood. Now, it's regulated by two hormones, both of them produced in the pancreas, insulin and glucagon. Insulin transports glucose in the body's cells, causing blood glucose levels to drop. Glucagon is the opposite. It stimulates the breakdown of glycogen in the liver into glucose and sends it back into the blood. What that does is it causes your blood glucose levels to rise. Remember, glycogen is stored in your muscle cells and it is stored in the liver. And so the pancreas will release these into the bloodstream, stimulates the liver or your muscles to break the glycogen back into glucose, increasing your blood glucose level so that you have the energy you need it when you need it. Okay. The feedback loop here shows a decrease in blood glucose level. Particular cells in the pancreas called the alpha cells will then respond by secreting glucagon. Glucagon will then transfer or move into your body cells, your muscle cells, and your liver cells, and then the response is the release of glucose from glycogen. Glycogen breaks down into glucose, and then that goes back into your bloodstream and increases your blood glucose level back up, therefore a negative feedback loop. The reverse happens if it is increased in blood glucose levels. Beta cells in the pancreas now will release insulin, and then they will secrete. The insulin will then travel to your liver cells and your body cells, and what that does is it converts glucose back into glycogen, dropping it back down, or your body cells will then take up more glucose from your bloodstream to bring it back down again if it's too high. Yeah, so you can see there a negative feedback loop regulating blood glucose level within a narrow range. Okay. However, this process doesn't always happen perfectly because in some people, a few conditions such as diabetes can occur. So we're going to spend a bit of time talking about diabetes and understanding sort of how diabetes affects a person. Okay. So here's a graph showing person A and person B in the glucose level concentration at the start. You can see here, right, that for person A, the blood glucose levels rises and then it will drop back down. For person B, it rises and it rises, keeps rising again, and then it drops again after a while. Now, of the two people, have a think, which one do you think has diabetes? Yeah, whether it's person A or person B, okay? And then we'll have a look at it later on, okay? But in terms of diabetes symptoms, high glucose level symptoms often stimulate a lot of thirst. People with diabetes often have to urinate frequently and they can get a blurred vision as a result of that. And the reason for that is because when glucose levels rise too much, it can rupture the cells in the eyes and then it causes blood to leak out of the eye and causes their vision to blur. Low glucose levels often result in low energy levels, fatigue, extreme hunger, and weight loss. And so you can see both are being really bad. There are two types of diabetes. You got type 1 diabetes, which is what we call juvenile diabetes, and type 2 diabetes, which is called onset diabetes. And they're both slightly different, even though they result in a imbalance of blood glucose levels. Okay, so type 1 diabetes is the production of insulin fails. The pancreas doesn't produce enough insulin, and the blood glucose levels rises too high. This is most common in children because they're often born with this version of diabetes, and they don't really know why, but there's some sort of genetic connection behind it, because if your grandparents or your uncles or your aunties have it, you've got a higher chance of having it. People with type 1 diabetes have to take insulin injections, and they have to monitor their blood glucose levels very closely and making sure that it sits within a certain range. Diet needs to be regulated. They need to take their insulin tablets or injections quite regularly to make sure that the body is able to still have enough insulin traveling around the blood and regulates that blood glucose levels, because the pancreas isn't making any of it, okay? And so that is an issue that they have to kind of live with for life, okay? Type 2 diabetes, however, is what we call onset diabetes, and this is when there is insulin resistance. The body doesn't respond to the insulin that is already being released, and so the blood glucose levels build up because the body's not taking the necessary responses. Okay, this is primarily due to issues such as obesity, and is partly preventable by lifestyle and dietary changes. And so you can prevent yourself from getting type 2 diabetes by monitoring your diet. So if you eat food that is too high in sugar over a long period of time, then you run the higher risk of getting onset diabetes, because your body then stops responding to the insulin that it's being produced, because it's been kind of worn out, so to say. And so 9 out of 10 cases of diabetes is often type 2 and is as a result of diet and lifestyle. Okay, and then the last one is the genetic basis. Okay, here's an interesting figure. You can see there a connection between the occurrence or the prevalence of diabetes versus mean body weight, right? The graph can seem a little bit confusing, but from the 1990s over to 2000, you can see that the mean body weight has increased. Yeah, the axis on the right refers to kilograms, which is for mean body weight, which is the blue. Yeah, mean body weight has sort of increased from about 72.8 all the way up to about 77.2 over the last maybe, I don't know, 40 years or so. And you can actually see the prevalence, or in other words, the occurrence of diabetes increase around about the same time. So yeah, from the 1990s, a slight dip in the 1990s, early 90s, and then it increases again to match mean body weight, which tells us that as people are getting larger, diabetes is occurring more frequently, particularly type 2 diabetes there. Okay. All right. So that's it. I hope you guys enjoyed that, and I will catch you guys next time. Okay.